Hi, I'm Pieter Gijsbers, and in this video I will present to you the AutoML benchmark. This is a paper that has been published in JMLR and is accepted to the journal track of the 2024 AutoML conference. First, I'm going to explain to you why we started the project in the first place, back in 2018. We saw that papers use an ad hoc set of datasets on which to evaluate their tabular AutoML models. Sometimes they would choose a very small set of datasets, such as this one, and this may make you question the generalizability of the results. The next paper would come along and use a completely different set of papers, which makes it hard to compare the results of one paper to the other. And the third one would make different decisions altogether, maybe evaluating, optimizing towards different metrics, using different time constraints, or make any other kind of change to the experimental design. This makes it super hard to compare the results across papers and also to track the progress of the field over time. We also see that sometimes there are some technical issues evaluating the methods that others have made. For example, when I make a new tabular AutoML method, I need to evaluate also the state of the art, especially since we're using a new benchmark every single time. And often there would be some installation or configuration issues, or use some incomparable setup. We also see that there were some issues with reproducibility. It wasn't always very easy to reproduce, not always open source, and sometimes it would be hard to get the data or the exact splits, etc. So we set out to tackle these issues, and we did this in our work, the AutoML benchmark, where we contribute a benchmarking seed of over 100 different datasets. We provide some guidelines on how to evaluate models on those datasets. We developed a software package that can do the end-to-end evaluation of tabular AutoML frameworks, and we conduct a large-scale evaluation to demonstrate all of this. Our benchmarking seed consists of over 100 tasks that includes binary classification problems, multi-class classification problems, and regression problems. We try to make them represent real-world challenges that tabular AutoML frameworks might face, so they span a wide range of dataset characteristics. For example, different dataset sizes, there are missing values in there are some categorical features which have a very high number of unique values, there are sparse datasets in there are imbalanced datasets in there, and so on. We also try to make sure that the datasets represented different domains. One big limitation that stems from the state of the AutoML frameworks at the time is that there are no text features in any of these datasets, as at the time there was almost no AutoML framework that supported this out of the box. We developed software that can run these experiments needed for the evaluation of an AutoML framework from the end to end. This includes loading the data, whether this is from disk or from OpenML, installing the AutoML framework and consequently invoking it, passing the data to it and the configuration, retrieving the results and processing them. And you can do all of this either locally, you can run your experiments in a container such as Docker, or even on AWS. The tool features many different AutoML integrations. An integration consists of a small number of scripts, primarily a shell script which can take care of the installation of the framework, and a Python script which can take care of the invocation of the framework. Note that the framework doesn't need to be written in Python. You can also call the command line from your Python script to invoke your AutoML methods. We have a number of different integrations stemming from academia and industry, covering a wide range of different methods. And we try to make these integration scripts in collaboration with the developers of the different AutoML frameworks to make sure that the tools are used correctly. All of this is of course available open source, and you can find the code and documentation on our GitHub. Here's an example. When we want to evaluate AutoScikit-learn on the benchmark, we can use this command, and it will evaluate it on the 71 classification tasks in our benchmark as they are defined on OpenML. It uses a 1 hour, 8 core constraint, and it executes the experiments on AWS with up to 100 parallel EC2 instances. Just using this command line gives you, in the end, the results of the whole benchmark. Now I want to show you some of the results that we obtained from our evaluation. But I want to give you two warnings first. The first warning is that we're only looking at the defaults of the AutoML frameworks or some kind of presets, which is an easy way to specify a different trade-off between the predictive performance and the inference time. You may get better results when you tune the AutoML framework for your problem. The second warning is that we'll be doing a little bit of time traveling. The results I'm about to show have been obtained well over a year ago in June of 2023. Some of the results even date from September 2021, in case the framework hasn't really changed between those dates. So with that in mind, please look at the suggested visualization methods more than looking at the actual results. Because if you were to repeat the experiments today, you would almost surely get different results because the AutoML frameworks have had updates since the experiments. First, we recommend that you give a nice visual aggregation of all the different results. One way to do this for the predictive performance results is to aggregate this with a critical difference diagram. This shows the average rank of the different frameworks. So for each dataset, the rank for each framework is determined, and then we take the mean of this. We can do a nice statistical test that shows whether or not the mean rank of the different frameworks is statistically significantly different from each other, as indicated by the thick horizontal bars. One drawback, however, is if many frameworks score very similar performance in absolute measures, then the ranks can still have large differences. So you should always complement a rank plot together with something that has a better representation of the absolute differences, such as the scale plots that we suggest here. So we need to scale the results so that the metrics are commensurable across all the different datasets, as every different dataset might have different scales for the log loss or root mean square error and so on. So we scale the results for each dataset between 0 being the random forest baseline performance and 1 being the best observed performance. Here we see, for example, that while we saw that T-Bot had the worst rank of all the frameworks, some of the other frameworks have a longer tail. And we see that many of the frameworks, at least at a glance, get very similar results to each other. We also look if there are different subsets of the results in which we see different characteristics of the performance. For this we use Bradley-Terry trees. And here we see, if we follow the left branches on the tree, that the results on small datasets are more similar to each other than ones on the large datasets that you can see if you follow the right branches of the tree. And we also say that you have to look at more than just the predictive performance. In our work, we look also at the inference time. We think it might serve also as a proxy for the model complexity, but you may also look at any other dimensions, such as specific fairness metrics, for example. We see here in our result that there is no one particular framework or preset which by itself always produces the model which both has the fastest inference time and the highest predictive performance. So depending on the use case, you might choose different models or different presets. We also look at when the AutoML frameworks misbehave. Sometimes our AutoML frameworks crash, and we see that this is for various reasons. Bugs in the software, problems with memory management, or other ways in which the systems freeze up and don't adhere to the provided time constraints. We also see on the right that larger datasets more frequently lead to this kind of behavior. We also see that there are two particular small datasets with a very small minority class, and these consistently leads to errors on specific AutoML frameworks. So sometimes the dataset characteristics matter. Once more, the results shown here were those obtained well over a year ago, and if you repeat experiments today, you're almost certainly going to get different results. It's important, however, to make sure that you evaluate AutoML frameworks among multiple axes and not just predictive performance. A big limitation about the way that we do our experiments is that you cannot draw conclusions about individual design choices. We're comparing the frameworks as a whole with changes in search space, optimization methods, and so on. So you can't attribute the performance to any individual aspect. The second thing is that we don't do any qualitative evaluation. For you, when you choose your AutoML framework, it may also be important what support is available, the documentation that's available, whether or not there's a user interface that shows you insight into the AutoML process or into the produced model, and so on. In the future, we also want to work on updating the benchmarking suite to make sure it represents the real-world challenges that tabular AutoML frameworks might tackle today. And for example, this includes including text features in those datasets. And we also want to look, for example, at multi-objective optimization, as you want to maybe optimize towards both the predictive performance and the inference time, and explicitly communicate this with the AutoML framework. We believe that the AutoML benchmark is a very useful tool for the community. And if you do so too, and you want to help us make sure that it is a success and it stays relevant, then you can do it very easily. You can start us on GitHub, and you can simply use the AutoML benchmark and talk about it. This already helps a ton. If you want to make some more concrete contributions, you can, for example, do so without coding anything by helping people on GitHub using the benchmark, writing more documentation, or suggesting new interesting datasets to include in the benchmarking suite. And of course, code contributions are also always welcome. We believe that the AutoML benchmark can be useful for the community for a long time to come. And if you're interested, then have a look at these links. They are in order: a contribution guide, the link to our software on GitHub, and the link to our paper on JMLR. So thank you very much for watching this, and I hope to see you around on GitHub or at the poster presentation.